Welcome class. We're looking today at percentage composition. You should have had a chance to go through this activity with some partners in the class where we looked at the percentage composition of water in popcorn. And the experimental design had us massing the kernels before they were popped, carrying out the reaction, I guess you could say, releasing that little bit of water inside and then massing the popped kernel sample without the water. So indirectly we were able to get the mass of escaped water, and then from that, knowing the initial mass of unpopped kernels here, we could calculate a percentage. And most groups found that the percentages range from 14 to 16%. And that is really an example of percentage composition. It's taking a particular substance and breaking it up into different components or fractions, and then evaluating the percentage of those by mass. Okay, when we evaluate percentage composition for compounds, we need to start with, again, a mass. In this worksheet here, we'll go through the calculation for carbon monoxide and carbon dioxide, and also we'll do a practice example in addition to that with water and hydrogen peroxide. So the law of definite proportions, or law of constant composition, is very similar. It just simply states that every compound has a fixed percentage by mass of its elements, and the element mass to the total unit mass will be constant for carbon and oxygen in carbon monoxide, but it will be different for carbon and oxygen in carbon dioxide. So in this example here, we see that to start this calculation, it's best to consider 1 mole. Now that we've looked at the molar calculations, we know how to work with molar mass. So we consider 1 mole, and we calculate the molar mass of each of the compounds. So we just add the relative atomic masses based on the number of atoms of each element, and we get our totals. The next thing we're going to do is take the percentage of each of the element masses to the total, and we find that carbon has percentages of about 43 and 27 respectively for those two compounds. So there's more carbon in carbon monoxide, which fits our understanding of the molecule. It's a 1-to-1 ratio of atoms, whereas carbon dioxide is a 1-to-2 ratio of atoms. And the rest of the mass, or the rest of the percentage, must be for oxygen. So we can calculate it directly using the mass of oxygen, or we could calculate it indirectly. And of course, we'll notice that these two numbers here add up to 100%. So we could easily find the second by subtracting the first from 100. So that's a direct calculation of percentage by mass. How do they compare? Well, we can certainly see that the percentage of oxygen in carbon dioxide is higher. So percentage composition as a definition here is just the mass percentage makeup of a compound by its elements. It can be determined 2 ways. Experimentally, we can determine it using measured masses in the lab if we have the elements' masses known. Theoretically, which is what we just did, we can determine it using calculations from a known chemical formula. So that's really important. We'll go through another example here using water and hydrogen peroxide. So in this calculation here, as you can record it as you're going through this video. First step I've done here is calculate the molar masses of each of the compounds, H2O and H2O2. Obviously, hydrogen peroxide has a heavier molar mass because of the additional oxygen atom. Water has percentage of hydrogen based on 2.02 grams of hydrogen contributing to the 18. So as a ratio, that is 11.2%. The percentage of oxygen can simply be found by subtraction. I'm underlining the third significant digit because the sum of hydrogen's relative atomic masses is known to 3 significant digits. So for division, we're carrying 3 significant digits. However, because I'm doing a calculation with that 11.2%, I'll just carry 1 more digit before I round my final answer to, in this case, 1 decimal place, so 88.8%. When I'm subtracting here, in this calculation, I'm going with decimal places. 100 has no uncertainty at all. It's That's a whole counted value, so I would report my answer to 1 decimal place. For hydrogen peroxide, do the same calculation for the ratios. Again, hydrogen's contribution to the overall mass is still at 2.02 grams for every mole of the compound. However, the total mass of 1 mole is now 34.02. So the percentage of hydrogen is lower now, at about 5.9%. And again, subtracting that from 100 to get 94.06%. Notice in the percentage oxygen for hydrogen peroxide, I'm carrying 3 significant digits, but in that case it happens to be 2 decimal places. So this is 3 significant figures or digits, but 2 decimal places. Because it's 2 decimal places, when I subtract, I carry 2 decimal places. So I would round to the nearest 100th. Whereas in the previous example, it was 3 significant digits or significant figures, but only 1 decimal place. So a slight difference in how we would report the digits for this answer. But again, composition compares in the same way as it did for CO and CO2. We would have a higher percentage hydrogen in water. So water, by molecule, has more hydrogen in it than does hydrogen peroxide.
When magnesium metal burns, the product of the reaction has a greater mass than that of the original magnesium. John Dalton's atomic theory successfully explained this seemingly strange result.
Okay, I included that clip for a couple reasons. We will be carrying out that identical reaction. So you saw someone holding a strip of magnesium ribbon with some tweezers or tongs, and it burns very brightly. And when it burns, chemical reaction takes place, which John Dalton understood. But he also looked at chemical reactions enough to know that the mass of a particular compound is unique because, or the percentages mass by mass is unique because of the different components. And so elements can combine with other elements to form new substances, and the ratio in their combination is constant. So a given amount of magnesium will react with a given amount of oxygen only when magnesium oxide is formed. You could take a different oxide and you would require different percentages of oxygen and, let's say, calcium. So we'll be burning magnesium in the lab. You'll need to read the procedure for investigation 451 on pages 180 to 181. You'll be working on some questions in class as well over the next couple periods, and those are found in your textbook in section 4.5. See you in class tomorrow.